Welcome back, gangies. We up dumb late. We're back though. The LC must be done, even though we're in midnight oil caveman hours currently. But I think we do have a comment. Yesterday we did a mobile session, and we gotta respond to our boy. So we'll hop over. We have a question from Khan Kunawat, legendary computer toucher, as well as part-time mountain climber. May I ask how long you're going to continue this LeetCode challenge? I plan to do it. Good question. I plan to do this or till the end of time. Also, when we finish all of the problems. Yeah, I'd like this challenge to end once you finish all the problems. Then we can put this to bed. And also, the LC devs will stop harassing us. The ideal outcome. But I think that's the ideal outcome. If we can get that going, I have no choice but to stop infiltrating the HCC. The hyperbolic coding chamber is being infiltrated by LC devs. They're planting some operatives to sort of try and disrupt the operation we currently have going. But fortunately, we have some commanders in place, as well as some rogue agents who are going to help us uncover these hidden operatives. So hopefully we can figure that out and foil yet another LC backend. The LC backend engineers are out for the Discord, so hopefully we can. It's a classic battle between light and dark, good and evil. HCC is neither. I think we're on the side of chaos. So that being the case, we solved the search in rotated sorted array yesterday. And I think the time complexity was log n. Basically, the problem was the array is sorted. I mean, it's rotated, also sorted. Want to find a target passed into the function. We're given an array of numbers and a target. Cannot locate the target. We should return -1. Can locate the target. Should return the index for which the target exists at. The core of this solution pretty much rests on using a binary search to find where the boundary point is, pretty much between. If the array is sorted in ascending order, we're going from 7 to 0 here, which means rotated 4 indices. So 0 is going to be our boundary point, right? And from there, we can pretty much do 2 binary searches, right? Or 1 if we check the elements. Either, if we're looking for target 0, we know that it either has to be greater than 0 or less than 7. Since our target is, we just search both halves of the array. Binary search, and this lets us about like 3 log n time in the worst case, which is basically log of n time. I'm gonna see if there's a better way. We pretty much coded this out on a phone. I'm gonna clean it up just real quick. And I think that looks of it should pass because it passed earlier. Or maybe this is the version we haven't fixed. For some reason, there are 2 versions. I guess the code is saved in your browser cache. The version we solved. Yeah. Okay. So that seems fine. Let's check out the solution. Oh, it looks like there's an editorial. So let's see. The approach 1 is the binary search. The problem is to implement a search in log of n time that gives an idea to use a binary search. The algorithm is quite straightforward. Find a rotation index is a better name for the variable index of the smallest element in the array. Binary search works just perfect here. Rotation index splits the array in two parts. Compare num sub 0 and target to identify which part one has to target. From a binary search in the chosen part of the array. If we look at the Python solution, we have a find rotate index function, right? While left is equal to right, we calculate the pivot. If num sub pivot is greater than num sub, wait, isn't that basically what we did? Num sub, we used a really actually complicated one. Num sub pivot plus num sub pivot greater. Check if the pivot before the if the pivot is greater than the next pivot, then this pivot must be the rotation index. Otherwise, num sub pivot is less than num sub left. Right down. Otherwise, move left equals 1. Then we actually implement binary search. Instead of going through the input array in 2 passes, we could achieve the goal in 1 pass with a revised binary search. The idea is that we add some additional condition checks to the normal binary search to better narrow down the scope of the search. As in the normal binary search, we keep 2 pointers, start and end, to track the search scope. Normal binary search, we keep 2 pointers, start and end, to track the search scope. At each iteration, we reduce the search scope in half. Okay, here are the detailed breakdowns of this algorithm. Initiate the pointer start to 0, and the pointer end to n-1. Perform standard binary search while star is less than or equal to n. Take an index in the middle. Pivot. If num submit target, the job is done. There could be 2 situations. Pivot element is larger than the first element in the array. Separate from the first element. It is non-rotated as following graph, or the pivot is greater than the last element. Yeah, my version is definitely crazy, but does get us where we need to go. So I think I'll take it for now. About 10 minutes left, so I think I'll try a problem with the time that remains. It looks like we're at 368 solved problems. Our medium count has increased, which is promising. We have a new problem. Find first and last position of element in sorted array. We have an array of integers and nums sorted in non-decreasing order, ascending order basically, with duplicates. Find the starting and ending position of a given target value. If target is not found in the array, return -1, -1. Let's write an algorithm with log of n time complexity. This seems like you could just, it's gonna sound crazy, but I think you could just binary searches. You want to find the start and end indices of target value. Interestingly enough, I think if we have a target value, we can just search for one less than that target value. This should put us at the, which would actually be sort of messy actually. If I search, for example, 7, the target is 8, I search for 7. It's possible we end up at its first 7 or the next 7. This is going to sound crazy, but I think we can fix that problem by searching for a ration or I guess a rational number. For example, if I search for 9, likely to end up, we have multiple. If let's just say we have let's just say, yeah, we're looking for the target 8. Let's say we search for 9, we search for 9, multiple 9s, we can end up on any side of that spectrum. So I'm wondering, let's just jot these ideas. B search with rational number, or B search with number plus 1. If we do that secondary binary search, let's just say we searched for 8, or we're searching for an index, the index is 8, and the next index is greater than, or I guess we're starting from the beginning, is the index is 8 and the index before it is less than 8. We calculated the midpoint of this, we have 4, 5, 6 over 2 would be 3, 0, 1, 2, 3 would get 8. The current index and we previous index, we would have 7. So we'd have index 3, which is perfect, right? Let's just say we were searching for something less directed, like 7, right? We check 8, like we check the middle index. The middle index, which should 3, is not equal to 7, so we're gonna have to set it equal to right. We're just gonna cut out all the values, right? The left, so right is gonna equal pivot. We can search the middle again. We're gonna have 0 to 4, 4 minus 2, over 1. We're gonna check 7. We're gonna check 7 at the first index. Check 7 at the first index, and from there we realize first index is 7, but the next previous index 5, which is exactly what we're looking for. So we return. Okay, I think we can actually do that. We have 3 minutes. We can do a function called bSearch. Right, we can do a function called bSearch front. Target is a number. We're going to return a number. We'll say left is equal to 0, right is equal to nums.length. Minus 1, left is less than or equal to right. Const pivot will be equal to math.for right minus left over 2 plus left. We'll say if num sub pivot equals target, right, and num sub pivot minus 1 is less than target, we can return pivot. Otherwise, we can say else if num sub pivot is less than target, we'll say else if num sub pivot greater than target, right is equal to pivot. Find it. We'll on you have to write one more called bSearch back. We're gonna get TLE again on this one. Might be the graders and the equals. So if we say, okay, num sub pivot, right, we get this 7 right here. Let's just say we got this 7, 5. It must be these other cases actually. I'm actually not following why. Oh, we're looking for 8. Yeah, I'm not following. Let me just print this. we'll return the pivot here. Otherwise, the rules change a little bit. We found the target that we're looking for, right? But we want to go towards the front. Basically, if the item is not less than it, we want to go left. Basically, say right to. We should be able to just copy this bsearch front function. Why is my window so? And then change it to back. Oh, and we'll change second one to be I think I'm problem. We should just be able to say start end, and I think the reason we haven't is secondary one should be pivot minus one is less than target. This should be plus one is greater than target. We're passing the first to bring back and here we'll put num sub 0 equals target 0 otherwise one. So I think we can fix this by just saying sub minus one is or one is the We just miss a plus. Oh man. Hopefully that's not the case. Oof. Oh man. B search is the worst. I think I'll keep an eye out going forward, but I have this problem. 30 minutes. We just spent 15 minutes debugging a plus sign. That's unfortunate, but we'll take the W. I think we'll stop there for today.